Welcome to our walkthrough of LeetCode problem number 1272, Remove Interval. In this problem, we'll explore how to modify a list of non-overlapping intervals by removing a specific interval. Stay tuned as we delve into the problem, break it down step by step, and discuss the solution in detail. Let's get started. The problem requires us to work with a list of intervals that are sorted and non-overlapping. Each interval in this list is represented as a two-element array, where the first element is the start and the second is the end of the interval. Along with this list, we are also given another interval called to be removed. Our task is to modify the original list of intervals by removing any portions that overlap with to be removed. The result should be a new list of intervals that remains sorted and non-overlapping, just like the original list. This process involves subtracting the interval to be removed from each interval in the list. The input consists of the list of intervals and the interval to be removed, while the output is the updated list of intervals after performing the removal. Let's look at an example to understand the problem more clearly. Suppose we are given the intervals 0, 2, 3, 4, 5, 7, and the interval to be removed is 1, 6. The output in this case would be 0, 1, 6, 7. Here's why: the first interval, 0, 2, overlaps with 1, 6, leaving 0, 1 as the remaining part. The second interval, 3, 4, is entirely contained within 1, 6, so it is removed completely. The third interval, 5, 7, partially overlaps with 1, 6, leaving the portion 6, 7. After processing all intervals, the resulting list is 0, 1, 6, 7, which is sorted and non-overlapping. Now consider another example where the input intervals are 0, 5, and the interval to be removed is 2, 3. In this case, the output is 0, 2, 3, 5. Here, the interval 0, 5 overlaps with 2, 3, but since the overlap is in the middle, the interval splits into two parts, 0, 2, and 3, 5. These two resulting intervals are non-overlapping and sorted, so the output list becomes 0, 2, 3, 5. For another example, let's take the input intervals 0, 10, and to be removed as 5, 10. The output here is 0, 5. The interval 0, 10 overlaps with 5, 10 at the end, leaving only the portion 0, 5. The resulting list of intervals is therefore 0, 5. This demonstrates that when to be removed overlaps with only one part of an interval, the remaining portion is preserved. Additionally, the constraints of the problem specified that the number of intervals can go up to 10 to the power of 4, and the interval values may range between -10 to the power of 9 and 10 to the power of 9. This wide range highlights the need for an efficient solution. The intervals in the input list are guaranteed to be sorted and non-overlapping, which simplifies the problem slightly. There are several edge cases to keep in mind. First, if the interval to be removed does not overlap with any intervals, the output will simply be the same as the input. Second, if to be removed completely contains one or more intervals, those intervals will be entirely removed. Third, if it partially overlaps with an interval, the interval may split into two separate parts. Additionally, if to be removed is entirely outside the range of all input intervals, no changes will be made. Finally, in cases where there is only one interval in the input, the behavior depends on whether to be removed fully, partially, or does not overlap with it. These scenarios ensure that we handle all possibilities when implementing the solution. To solve the problem of removing a specific interval from a list of non-overlapping, sorted intervals, we need a strategy that efficiently identifies and handles overlaps. One such approach is the brute force method. The intuition here is straightforward: iterate through each interval in the input list and check if it overlaps with the interval to be removed. If no overlap is detected, the interval remains unchanged and is added directly to the result. If there is an overlap, we carefully calculate the portions of the interval that lie outside the range of the interval to be removed. These non-overlapping segments are then added to the result. The key steps for this approach involve performing overlap checks based on the conditions end to be removed, 0, and start to be removed, 1, and then splitting the interval into segments if necessary. This process ensures we handle every interval in a single pass, giving a time complexity of O(n), where n is the number of intervals in the list. Although the brute force approach is efficient, it's important to consider if alternative methods could optimize the solution further. One such alternative is leveraging binary search. Since the intervals are already sorted, binary search can help quickly locate the first and last intervals that might overlap with the interval to be removed. This would allow us to limit processing to just these potentially overlapping intervals. After narrowing down the range, the same checks and splitting logic from the brute force approach can be applied. However, while binary search reduces the initial search space to O log n, we still need to process overlapping intervals, which can take O k time, where k is the number of overlapping intervals. In the worst-case scenario, where most intervals overlap with the interval to be removed, this alternative ends up being O n overall, just like the brute force approach. Furthermore, the added complexity of implementing binary search doesn't yield significant performance improvements. Therefore, the brute force method remains the preferred choice due to its simplicity and direct alignment with the problem's requirements. To finalize our approach, it's crucial to recognize the key observations that make the brute force method the optimal strategy. The most critical insight is that the input list is already sorted and contains non-overlapping intervals. This allows us to process intervals sequentially without needing additional steps like sorting or merging. Splitting intervals based on the portion outside the interval to be removed is a straightforward operation, and since we only process each interval once, computational overhead is minimized. The aha moment here is realizing that the overlap check and splitting logic are sufficient to solve the problem efficiently. When comparing trade-offs, the brute force approach stands out for its simplicity and the lack of any need for additional data structures or pre-processing. Although binary search might seem appealing, it introduces unnecessary complexity without providing tangible benefits. The final complexity of our chosen approach is O n in time and O n in space, making it both optimal and well-suited for the constraints of the problem. To solve this problem, we need to modify a list of non-overlapping, sorted intervals by removing any portions that overlap with a given interval to be removed. The result should also be a list of non-overlapping, sorted intervals. First, let's define the input and output. The input consists of a list of intervals, where each interval is represented as start and end, and these intervals are guaranteed to be non-overlapping and sorted by their start times. We are also provided with a single interval, to be removed, which specifies the range we need to remove. The output will be a modified list of intervals where any overlap with to be removed has been removed, and the resulting intervals remain sorted and non-overlapping. To achieve this, we start by initializing an empty list, result, to store the intervals after modification. Then, we iterate through each interval in the input list to evaluate its relationship with to be removed. Depending on how the current interval interacts with to be removed, we will decide whether to include it in the result list and, if so, whether to adjust its boundaries. When examining the relationship between an interval and to be removed, we encounter three main cases. In case 1, there is no overlap. This occurs if the interval is entirely before or after to be removed. Specifically, if the end of the interval is less than or equal to the start of to be removed, or if the start of the interval is greater than or equal to the end of to be removed, then the interval remains unaffected. In such scenarios, we simply add the interval to the result list as is. Case 2 deals with partial overlap. Here, only part of the interval lies outside of to be removed. To handle this, we calculate the non-overlapping segments. If the start of the interval is less than the start of to be removed, the segment, interval, 0, to be removed, 0, is added to the result list. Similarly, if the end of the interval is greater than the end of to be removed, the segment, to be removed, 1, interval, 1, is added. Finally, in case 3, the interval is fully contained within to be removed. This means the entire interval lies within the range of to be removed, so we exclude it from the result list entirely. After processing all intervals, the result list is returned. Several insights make this algorithm efficient and manageable. First, the input intervals being non-overlapping and sorted simplifies the problem significantly. Because of this structure, we can process each interval linearly without worrying about merging intervals after removal. This ensures the logic remains straightforward. Next, let's consider key edge cases. For instance, to be removed might not overlap with any interval, in which case the output is identical to the input. Alternatively, an interval might be fully contained within to be removed, requiring its removal. Another edge case is when to be removed partially overlaps with multiple intervals, meaning we need to adjust segments from more than one interval. Finally, to be removed could extend beyond the range of all intervals. It's also important to note the efficiency of our approach. The algorithm processes each interval once, performing constant time checks and updates, leading to a time complexity of O(n), where n is the number of intervals. The space complexity is O(n) as well, because we use a list to store the result, which in the worst case could contain all the original intervals. Let's walk through an example to see the algorithm in action. Suppose the input intervals are 0, 2, 3, 4, 5, 7, and the interval to be removed is 1, 6. First, we process the interval 0, 2. There is a partial overlap, as 1, 6 intersects with this range. The non-overlapping segment 0, 1 remains, so we add 0, 1 to the result list. Next, we evaluate 3, 4. This interval is fully contained within 1, 6, so it is skipped entirely. Finally, we process 5, 7. Again, there is a partial overlap, and the remaining segment, 6, 7, is added to the result list. After processing all intervals, the final result is 0, 1, 6, 7. This output satisfies the requirements: the intervals are non-overlapping, sorted, and any overlap with 1, 6 has been removed. To conclude, let's analyze the algorithm's complexity. The time complexity is O(n), where n is the number of intervals. This is because we iterate through each interval exactly once, performing constant time operations for each. The space complexity is O(n), as we store the resulting intervals in a list. In the worst-case scenario, the result list could contain all the original intervals if none are removed or modified. This efficient use of time and space makes the algorithm well-suited for handling large input sizes while maintaining clarity and correctness. The solution to LeetCode problem number 1272, remove interval, involves iterating through the list of intervals and handling 4 distinct cases for each interval relative to the interval to be removed. The function removeInterval takes 2 inputs, intervals, a sorted list of non-overlapping intervals, and to be removed, the interval to remove. It outputs a modified list of intervals after removing portions overlapping with to be removed. Step-by-step explanation of the code asterisk. 1. Initialization. We start with an empty list result, which will store the updated intervals. 2. Iterating through intervals. The for loop processes each interval, start, end, in intervals. 3. Case 1. No overlap. Before, if the end of the current interval is less than or equal to the start of to be removed, the interval is completely before to be removed, so we directly add it to result. For case 2, no overlap. After, if the start of the current interval is greater than or equal to the end of to be removed, the interval is completely after to be removed, so we also add it directly to result. 5. Case 3, partial overlap. Left, if the current interval starts before to be removed but overlaps partially, we add the portion, start, to be removed, 0, to result. 6. Case 4, partial overlap. Right, if the current interval ends after to be removed but overlaps partially, we add the portion, to be removed, 1, end, to result. 7. Final result. After processing all intervals, we return result. This approach ensures that the output intervals remain non-overlapping and sorted. The time complexity is O(n), where n is the number of intervals, as we iterate through the list once and perform constant time operations for each interval. Here, we begin the implementation of the removeInterval method, which takes in a list of intervals and a specific interval to be removed. First, we create a list to store the resulting intervals after the removal operation. Then, we iterate through each interval in the intervals array. For each interval, we extract its start and end points. We handle 4 possible cases. In the first case, if the end of the current interval is less than or equal to the start of the interval to be removed, it means there is no overlap, and the current interval is completely before the interval to be removed. So, we simply add it to the result list. In the second case, if the start of the current interval is greater than or equal to the end of the interval to be removed, it means there is no overlap, and the current interval is completely after the interval to be removed. Again, we add it directly to the result list. Now, we address the cases where there is some overlap. If there is a partial overlap, we handle it by checking the boundaries. For example, if the start of the current interval is less than the start of the interval to be removed, it means there is an overlap on the left side. In this situation, we add only the portion of the current interval that ends where the removal interval begins. Similarly, if the end of the current interval exceeds the end of the interval to be removed, this indicates an overlap on the right side. Here, we add the portion of the current interval that starts where the removal interval ends. Once all intervals have been processed, we return the result list containing the updated intervals. This approach ensures that we account for all possible cases of overlap and handle them efficiently. Comprehensive walkthrough covering multiple examples with detailed state tracking and reasoning, 2 to 3 minutes, approximately 300 to 450 words. The time complexity of this solution is O(n), where n represents the number of intervals in the input list. This is because the algorithm iterates through each interval exactly once, making it a single O(n) loop. For every interval, the algorithm performs a constant number of checks, such as determining whether the interval lies entirely before, entirely after, or partially overlaps with the interval we want to remove. These checks are simple comparisons and take constant time, or O(1), for each interval. When there's a partial overlap, the algorithm may add 1 or 2 new intervals to the result list, which is also an O(1) operation per addition. By combining the single iteration over n intervals with these constant time checks and operations, the overall time complexity simplifies to O(n). This ensures that the algorithm processes the input efficiently, regardless of the specific intervals provided. The space complexity of the solution is O(n) in the worst-case scenario. This is primarily due to the output list, called result, which stores the intervals after processing. In the worst case, if the interval to be removed does not overlap with any of the input intervals, all the original intervals will be added to the result list. This means the size of result could be as large as the input list, requiring O(n) space. The algorithm does not use any additional data structures, and it processes the input list in place, so there is no extra memory overhead apart from the output list. Temporary variables, such as those used for looping, require only constant space, or O(1), which does not depend on the size of the input. Combining these factors, the total space complexity is determined by the size of the result list, making it O(n) in the worst case. To analyze the best, average, and worst case scenarios, let's start with the best case. If the input list of intervals is empty, the algorithm doesn't perform any operations, resulting in a time complexity of O(1) and a space complexity of O(1). In the average case, where the input contains a mix of overlapping and non-overlapping intervals, the algorithm still processes all intervals with a time complexity of O(n) and a space complexity of O(n). In the worst case, when the interval to be removed does not overlap with any of the input intervals, all intervals are added to the result list, but the time complexity remains O(n), because each interval is processed once, and space complexity also remains O(n), due to the size of the result list. Comparing this with a naive approach, which might involve nested loops to manually handle overlaps, the current algorithm is far more efficient. While both require O(n) iterations, the naive approach might introduce unnecessary overhead during overlap checks and slicing. The memory usage would also likely be similar, as it depends mainly on the size of the result list in either case. This solution is optimized because it minimizes the number of operations by directly comparing intervals and avoiding redundant checks. Each interval is processed exactly once in constant time, O(1), ensuring no unnecessary computation. Unlike approaches that might rely on nested loops or intermediate data structures, this algorithm remains streamlined and avoids adding complexity. To mathematically prove its efficiency, let n represent the number of intervals in the input list. The algorithm iterates over these n intervals, performing a constant amount of work for each iteration, resulting in O(n) operations. In terms of memory, the space usage is primarily determined by the size of the result list, which is proportional to the input list size in the worst case. Therefore, the space complexity is also O(n). By balancing both time and space efficiency, this algorithm achieves optimal performance for the problem. When solving the remove interval problem, there are several common mistakes to watch out for. First, overlapping logic errors can occur if you don't properly handle cases where the interval to be removed partially overlaps with an existing interval. For instance, if the removal starts or ends inside an interval, you need to carefully adjust the remaining parts. Always think about all possible edge cases, partial overlaps on the left, on the right, or even complete overlap scenarios. Another common mistake is modifying the input list directly while iterating over it. This can lead to runtime errors or skipped elements, so it's safer to use a separate list to store your results. Additionally, there's the issue of inclusive versus exclusive bounds. If you confuse whether the interval boundaries are inclusive or exclusive, it can result in incorrect outputs, so be meticulous with these calculations. Don't forget that non-overlapping intervals must be preserved. Assuming all intervals overlap and removing everything is incorrect, you need to carefully check for intervals that don't interact with the removal at all. Finally, consider efficiency. Using nested loops is unnecessary here, as a single linear pass through the intervals, leveraging their sorted nature, is sufficient to get an optimal O(n) solution. This problem is not just about finding a solution, it's about demonstrating a deep understanding of interval manipulation and handling edge cases. A key insight is to approach overlap scenarios systematically. For example, think about what happens when the interval to be removed is completely outside the range of the given intervals. Or, what if it spans multiple intervals? You should also be ready to handle cases where the removal represents just a single point within an interval. During interviews, it's crucial to clearly communicate your thought process. Ask clarifying questions about constraints, like whether the intervals are sorted or if the bounds are inclusive or exclusive. This problem shares similarities with several other interval-based challenges. For instance, LeetCode number 56, merge intervals, requires merging overlapping intervals, while number 986, interval list intersections, focuses on finding intersections between two sets of intervals. You might also find number 435, non-overlapping intervals, interesting, as it involves minimizing the number of intervals to remove for a non-overlapping set. Finally, number 1288, remove covered intervals, is another related problem where you identify and remove intervals that are completely covered by others. These related problems can help you refine your skills further. There are a few alternative approaches to solving this problem, each with its own trade-offs. The most common and straightforward method is an iterative check with conditions. Here, you iterate through the list of intervals and determine the relationship of each interval to the one being removed, whether there's no overlap, partial overlap, or complete overlap. This approach is efficient, with a linear time complexity of O(n), but you need to be very careful with edge case handling to ensure correctness. Another approach involves binary search, which can be useful if the list of intervals is extremely large. By using binary search, you can quickly locate the first interval that overlaps with the one to be removed. While this can save time for sparse intervals, it adds implementation complexity and still requires the intervals to be sorted. Finally, there's the divide and conquer approach, where you split the intervals into two halves and process them recursively. However, this is generally overkill for this problem and less efficient than a single linear pass. The key takeaway is that the optimal solution lies in a simple greedy approach, iterating through the intervals once and applying clear conditions to handle overlaps. This makes the problem a great test of your logical thinking and ability to handle edge cases efficiently. Thanks for joining us on this journey through LeetCode problem number 1272, remove interval. We reviewed the problem, applied a logical approach, and discussed key insights along the way. Remember to practice similar problems to strengthen your understanding of interval-based algorithms. Don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!